So here I'm going to review Gaussian elimination, which is the standard method that we teach for solving linear systems of equations. I'm going to do it with all the arithmetic being done in MATLAB, just because MATLAB is better at arithmetic than I am. You can also follow along. It's the exact same example that's in section 2.3 of the book, so you can follow along in there as well. So here's a definition of a 4x4 linear system. AX equals B. So A and B are given here. And what we normally teach you to do is create a matrix Z. I'm calling it Z here. In linear algebra we call this the augmented matrix for the system. It contains the columns of A plus an extra column for the right-hand side vector B. So this is what we call Z. It represents the whole system. And the goal of Gaussian elimination, or the idea behind it, is to convert this system to a triangular system that we can solve, having the same solutions. And the mechanism for this is to essentially manipulate the matrix in such a way that we introduce zeros. So the system we're going to aim for is upper triangular, and what we do is we start in the first column by putting zeros here below the diagonals. Then we'll work on the second column, the third column, and then we'll be done. Okay, and the way we introduce zeros is by doing row operations. Because row operations represent adding multiples of equations to other equations, and that leaves all the equations just as true as they were before. So to put zeros in that second column, right, if we just look at the numbers, we know what we have to do. So we know that 2 times the first row, if we add that to the second row, will eliminate that -4. And -1/2 times the first row added to the third row, we'll put a 0 in that spot, and so on. So the way we can systematize this is, instead of converting those factors, computing those factors like 2 and 1/2 and 1 and so on, instead of doing those in our head, we'll just let the computer do them for us. So in order to put a 0 in the second row of the second column, we define this alpha, which is a row multiplier. Right? And if we take alpha times the first row, well, then we know that the first entry of that vector will be Z21, because we take alpha times Z11 and you just get Z21. So if we subtract that from the second row of Z, we'll put a 0 in that 21 spot. So this construction forces a 0 here. Okay, now in order to do to continue down this first column, in the third row we have a new multiplier. So this is the multiplier for row 3, because when we multiply that by Z11 in the first row, we'll eliminate the Z31 entry. So this forces Z31 equal to 0. Then we do it again for row 4, which forces Z41 to be 0. And that changes some of the other entries of the matrix, but we do now in fact have the beginnings of our upper triangular structure. The first column is now all set for an upper triangular matrix. Now we want to continue from here in the other columns without wrecking what we've done in the first column. So from now on, we actually leave the first row out of it, right? Anytime we added a multiple of that row to a lower row, we're going to destroy those zeros we just worked to put in. So we can't do that anymore. But what we can do is now move on to the second column. put zeros here, force zeros here, using multiples of row 2. And the clever bit about that is that we no longer we won't change anything about the zeros in column 1 because we already have a 0 there in row 2. So we'll just keep adding zeros in that first column. In fact, we can just ignore the first column from now on. So this does not change column 1. Okay? But before we go on to do that, let's go back, let's rewind. Let's go back to the original augmented matrix, okay? And what we're going to do is, since we're doing row operations, right? Remember, row operations are the same thing as multiplication on the left. Multiplying by a matrix on the left takes linear combinations of rows. That's exactly what we mean by a row operation. So we're going to do the exact same operations, but matrix style. So you go back, and what we did, right, is we computed 3 multipliers, alpha, alpha, and alpha. None of them depended on any of the others. So we could do them all at the same time. So what we do here is we compute all 3 row multipliers at once. And we put them into a particular matrix, which we now call L. So why is L the right thing? Well, remember that what we're going to do is take linear combinations of rows when we do L times Z. So right, this says just give me Z1, the first row back. 1 times that plus 0 times everything else. The second row of L times Z tells us to do 2 Z1 plus 1 times Z2 and put that into the second row of the result. That's exactly what we did above, with the alpha multiplier being 2. Okay, the third row says to take minus 1/2 Z1 plus 0 C2 times Z3 and put that into row Z3. And the bottom row says to take 1 times Z1 plus Z4. So you see how every row has this. Every row of L has exactly 2 non-zeros. One of them is always a 1 sitting on the diagonal. That's why I started out L as an identity matrix. Right? That's what this line was about. Okay? So that's because we're always taking a row plus some other row and adding it in. And all the other non-zeros are in the first column, right? Because we're doing row operations by adding multiples of that first row. So all those land in the first column. So if we do Z equals L times Z, we get the same Z as before. With the zeros forced into the first column. Now we're ready to go on into the second column. And we're going to do it with a matrix from the start. So again, we're going to multiply on the left by another matrix, which we'll call M. And M is going to leave the first two rows alone, and then it's going to add multiples of the second row into the rows below it. So you can almost guess, or you can almost just stare at this thing and see what M has to be. So I need minus 3 times the second row added to the third row, and then I don't need to do anything at all to the fourth row. So again, M has 1s on the diagonal. Okay, and it has a minus 3 here because we have to take minus 3 times the second row and add it into the third row. And that becomes the new third row. All the other rows are left alone. And so indeed, after multiplying on the left by M, we have zeros in the second column. Repeat that for the third column. We have an N with 1s on the diagonal, and just a single 2 in the 4-3 position, because that takes 2 times the third row, adds it to the fourth row to get rid of the 6 there in the fourth row. And now we've forced a 0 into the third column. The result is upper triangular. And therefore we can use backward substitution. So MATLAB style is to take this part as the system matrix now. Remember, this is an augmented matrix. So that's what we call now U for upper triangular. This column represents the new right-hand side in our equivalent linear system. So we peel that off into a vector that we call C. And then we do U backslash C, which MATLAB knows to do as backward substitution. So that's a solution of our upper triangular system. It's also a solution of the original system because the upper triangular system was equivalent, and we can do that by checking, right? Check that B is equal to AX. So the way we do that is we take the difference between the two, and that's called something that we call the residual by definition. And here we see it's exactly 0 because the numbers involved are integers. I just want to introduce one last definition. So we say a matrix is unit lower triangular. Means the matrix is lower triangular and 1s on the main diagonal. So those are exactly the matrices that we got as our row operation matrices. Are all unit lower triangular. The L, the M, and the N. Here's L, 1s on the diagonal, lower triangular. M, same thing, 1s on the diagonal, lower triangular. And N, 1s on the diagonal, lower triangular. So these are all unit lower triangular matrices.